Let us discuss this question. A woman draws water from a well using a fixed pulley. The mass of bucket and water is given together as 6 kg. The force applied by the woman is 70 Newton. We need to calculate the mechanical advantage. Now, here I have drawn a diagram. Here we are putting an effort of 70 Newton and we are able to pull this weight upwards. So how much force we are applying here, right? So to pull this up, we need to apply upward force of 60 Newton. So we'll apply this formula. Mechanical advantage is load by effort. We are able to pull up this load 60, but we need to apply 70 Newton of force. So the advantage we are getting is of 6 by 7. And we solve this fraction, we will get 0.857. So we can easily, just by seeing numbers, we can calculate the mechanical advantage. But what does that mean? So let us discuss these results going further. It tells us that machine is not idle. Otherwise, we'll be able to pull 60 Newton by 60 Newton. But here we need to apply more force. Why? Because maybe, let me use different color, maybe some force is we need to apply to overcome this friction, right? Rope with the pulley. And also if this rotates here, the pivot is there, right? So that friction also is coming into the picture. So we have to factor into that also. That's why we have to put more effort to compensate for this. So this is a practical machine. It is not an ideal machine. That's why the mechanical advantage we are getting is lesser than 1. Otherwise, in a fixed pulley, in ideal, it will give you the mechanical advantage of 1. You should be able to pick up 60 Newton with 60 Newton, but only in the ideal condition. If it is a practical machine, you have to compensate. We have to factor into the frictions which we are involved. Okay, so this is what we can discuss about the result. If we see like how we can approach by text, it tells us that the machine is not idle. Eta is the efficiency, is mechanical advantage divided by VR. For fixed single pulley, VR is equal to 1. Velocity ratio is 1. So eta will be equal to MA divided by VR. We don't write, let's say 1, we'll say eta will be just equal to mechanical advantage. So our efficiency is 0.857 or 85.7%. So we can say only 85.7% of total input is getting converted into the useful work or the output. So 70 Newton, if you multiply it by 0.857, or you take a percentage of it, 85.7 percentage of 70 Newton, you will get exactly 60. The rest, where it is going, is dissipated, overcoming friction or other forms of energy, like it can be heated, maybe some cranking sound. If you see the pulleys when they are moving, they make some sound. So that also takes up our energy. So that can also happen. Let's go to the next question. A fixed pulley is driven by 100 kg mass falling at a rate of 8 meter in 4 seconds. So they have given a distance and also how much time it takes to fall. It lifts a load. Calculate the power input of the pulley taking the force of gravity on 1 kg as 10 Newton, the efficiency of pulley, and the height of which to which the load is raised in 4 seconds. So let's go step by step. First thing, let's calculate how much we are putting in, how much power we are putting in. So we have a very simple formula, right? So we know effort force is of 100 kgf or 1000 Newton because I'm taking G as 10. So if we want to convert 100 kgf into Newton, we just need to multiply by G. So I'm taking G value of G as 10. So it will be 1000 Newton. Now the speed of or effort velocity will be 8 meter in 4 seconds. Can we say? Yeah. See, 8 meter in 4 seconds. That's what it is given in our question. So we can calculate the speed of the effort we are putting in. So that speed is given. The V is given, right? Now we know the force here and we know the velocity. So we have a formula to calculate power. Here the power input will be force into velocity. So that will be equal to come as 2000 watts. So that way we can calculate very easily that how much power input we are giving. So this is the 100 kg diagram and we are pulling it downwards. It travels 8 meter in 4 seconds. So we know the velocity of it, which was 2 meter per second. And then we multiply by this force. Force into velocity, we will get the power input. Now let's see how we can calculate the efficiency. So efficiency is power output divided by power input. So power input we already have calculated as 2. See here, we have already calculated that how much power we are giving in, but we don't know power output. So let's calculate that. So we need to calculate power output first to calculate efficiency, right? So this becomes our one more step here. Let's apply the same formula. Force output will be force. Now this will be what, for which force? The load into velocity. Let's go to the diagram. See, here's the load, 70 kg F we need to fight, and we have to go upwards. So we'll be, pulling it upwards. So it will have the same velocity, right? It will have the same velocity because there is only one fixed pulley here. That only changes the direction. It cannot change the speed of the load and effort. You'll understand this in detail, but we can calculate power output here as 750 into 2. Again, I'm taking G as 10. So we are getting 1500 watts. So now let's calculate the efficiency. Efficiency will be power output divided by power input. 1500 we are getting. We are putting in 2000 of effort and we are getting the 0.75 or 75% efficiency. Here is one a note here, like here they said a kind of a different way how to take the value of G, right? So they are saying the power input of the pulley taking the force of gravity on 1 kg as 10 Newton. So when if there is a 1 kg, let's say, let me have some space here, 1 kg, okay, 1 kg. When it will have 1 Newton, 10 Newton force, of course, you are calculating mg, right? Mg. So if they're saying that the force of gravity on 1 kg as 10 Newton, it means that m is 1. So what is g? G is 10. So this is an indirect way of saying to us, giving us a hint that we have to take g as 10, right? Let's say, let's go ahead. And also, if you see for the fixed pulley, if I take this down, because the rope cannot be stretched. So whatever distance I am taking it down, the load will move up with the same distance. So that is our next question, the height to which the load is raised in 4 seconds. So if it 4 seconds, this rope is going down by 8 meter, this has to be risen to the 8 meter height. If it is not, there is something wrong with that rope, right? It is stretching. So that should not happen. So in a single fixed pulley, this will be the case. The VR velocity ratio is 1, or the effort distance will be equal to the load distance moved. So this is where we have solved it, calculating height to which the load is raised. For a single fixed pulley, the velocity ratio is 1. It means the distance covered per unit time by the effort and load will be same. So distance covered by load will be also 8 meter, and they are asked in 4 seconds. So same thing, same velocity they will have. Okay, let's go to the next question. A single fixed pulley is given to us and a movable pulley is given. Both are used separately to use the lift a load of 50 kgf to the same height. Same height. Compare the efforts applied in an ideal situation. So this is a very good hint that they're telling take it as ideal. So now what we can do, let's go step by step. First thing, effort required in case of fixed pulley. A single fixed pulley only changes the direction, not the magnitude. It is not the force multiplier. It is not like I have to, pull it with the lesser force. It is not like that. Hence, we need to apply the same force of 50 kgf. Now you'll say, sir, what about friction, right? What about sound dissipation of energy? See, they have cleared this point here. Ideal situation, we have to think. In ideal situation, we don't have to factor into the friction. We will think that we have the best pulley in the world. Okay. Effort required in case of movable pulley. So now in movable pulley, you can think it like that. Now, if, for example, you have to pull it upwards alone, like you are here and you have to pull some weight upwards, right? This is the weight, let's say. So how much you have to, pull up, apply the force W, right? What if your friend comes here, right? So now you'll say, sir, they'll be sharing the load, right? So now if you ask how much you are applying, how much you need to apply the force, you will say, I am applying half of the force, right? So that is what the intuition with the movable pulley. So because there are two strands here supporting the load, so that's why we just need to apply half of the force required to pull. So if it is 50, can you tell me what will be the half of 50? Yes, we just need to apply 25 because it is a force multiplier. It has a mechanical advantage of 2. That is why we need to apply only half of the force. We will apply 25, it will get multiplied and become 50 to pull up this load. Okay, let's read it. In case of movable single pulley, the effort will be halved as the mechanical advantage of movable in pulley in idle condition is equal to 2. You can make your force double 2 times. So, or you can apply simple mathematics like if you see this diagram. So here we are applying the tension, here we are applying the tension. So 2T are supporting this one. So, or mathematically we can write 2T is equal to 50 kgf. So we can think of how much tension it is, 25 kgf, and that is what the tension is, our effort which we are putting. Also one thing we can notice here that we can also draw this diagram like this, right? We don't have to apply like when pulling upwards it looks somewhat weird in a sense, like who applies like that force. Can we make it more comfortable, more convenient? So we can use this fixed pulley, right? We can use a fixed pulley to change it to the conformable comfortable direction. Like this we are able to pull downwards. In this case also we will get the same mechanical advantage of 2 because still this load is getting supported by 2 strands, and whatever effort we put, that becomes a tension in this rope, but here it becomes 2, right? So it's the same thing. You can draw the diagram like this or you can draw the diagram like this. It's your choice, but both will give the same advantage. So because movable pulley, we have to apply half the weight. That's why the ratio, if you see, we need to compare. So we will take the ratio. So the ratio will become, in the first case, in case of fixed pulley, we need to apply 50. And in the second, we have to apply only 25. So the ratio will become 2:1. Okay, let's go to the next question. In a block tackle system consisting of 3 pulleys, a load of 75 kgf is raised with an effort of 25 kgf. Okay, we need to find a mechanical advantage, the velocity ratio, the efficiency. Let's go one by one. First thing, when they say a block and tackle system of 3 pulleys, it means 3 pulleys are distributed between two blocks. So block and tackle system always have two blocks. And the common and general arrangement which we will take is two pulley in one block, fixed in the upper block, and one pulley in the lower block. Yeah, movable, which is moving. And this is like a diagram we need to show. So the diagram will be like that. So this is fixed. This is one block. So this will be called. That's why it's called pulley block and tackle system. So these blocks they are talking about, and this is one block, right? This is one block. And what is the tackle? Tackle is a fancy name for this rope. So this is what we call a tackle. So here it is a block and tackle system. Okay, and you can start how to do that, wind the rope. That is very important. We apply the load downwards, this side, right, this side downwards, or you can keep it like this, not a problem. I'm just pulling it this side so that it is comfortable to draw. Nothing, it is just for convenience of drawing, nothing else. So I can draw like this also, straight downward. And then I'll go block by block. Like I'll go like this, go to another block, come here back and down. This is left, another block I went, and then another block, second block. So visit block by block, you will understand this. Never overlap. Okay, we have some guidance hints which we will be discussing in further questions when they get a little complicated. Also, when you are drawing, you can draw like this or you can draw like this. I have kept the end like this. So again, the simple guidance is we'll put effort like this, then we'll wind up, we'll go block by block. This is my first block. Let me put the blocks so we understand what I'm saying. So this is the second lower block. So now let me put the tackle. So I'll go for the first block, taken one pulley, went to the second block, go back to the first, go back to the second and tie it here. Right, that's how we will approach, because this they can ask, they can give you some pulley system and ask you to put a tackle on the block and tackle system, and this is a great skill to have, because otherwise people will get confused, like whether I should keep only on the left, only on the right, how many pulleys down, how many pulleys up. So there are some guidance and practice needed to draw the block and tackle system. Now we are pulling up 75 kgf, right? And if you see what we can observe is tension throughout the probe will be same. First thing is that. So whatever effort we are putting, that will be same everywhere. So this rope will have the same tension. So note that. So T is equal to E, right? That is that should be very clear with us. So tension is generated by effort. How much you will pull it, that much it tensed this rope will be. Here, three rope segments with tension T are picking up the load, right? So how we are seeing it? So see this part, right? How many strands of the tackle are supporting the load? So here it's a load downwards this side, but the upwards, if you see, there are three strands. One is here, second is this, and third is this. So there are three strands which are supporting this load. So this becomes important because this gives us clearly the velocity ratio. Let's go ahead. Let's calculate the mechanical advantage, because it is clearly given how much load and effort we are putting. From there, we can calculate that it is 3, because we are pulling 75 kgf with only the effort of 25. So the advantage we are getting is 3. Now let's go next. The velocity ratio. Okay, the velocity ratio. So the velocity ratio is a number of strands we need to count in the block and tackle system. How much they are supporting the load. How many strands are there which are supporting the load? So here it is 3, 3, right? Now, what they're asking, the efficiency. So efficiency, if you see, we have a formula, eta is equal to ma divided by vr. 3 by 3 is 1. So that's why this is an ideal machine, right? We have assumed that this is an ideal machine. That's why MA is coming equal to velocity ratio. In practical machines, that doesn't happen. Mechanical advantages in practical machines is always lesser than the velocity ratio. Let's go to the next question. A block and tackle system has 5 pulleys. If an effort of 1000 newton is needed in downward direction to raise a load of 4500 newton, calculate the mechanical advantage, the velocity ratio, and the efficiency of the system. So same thing, first is very easy. The load and effort is given. Just put in the formula load by effort. We are getting advantage of 4.5. So it means our force is getting multiplied by 4.5. That much weight we can pull up. So if I'm putting 1 newton of effort, I can pull up 4.5 times of that load. I can pull up 4.5 newtons. So that intuition, this value gives mechanical advantage. Let's see the velocity ratio. For velocity ratio, we need to be good at diagrams and we need some guidance. Like for example, there are 5 pulleys and we go on starting like this, 2 pulleys here and 3 pulleys here. This is not a convenient thing to do. Why? Because here are 3 pulleys. And why we are saying like we cannot have 3 pulleys here, but we can have 3 pulleys in the fixed block. Because see, when we are applying more pulleys in the lower block, we have to pull this also, this also, this also, this also with the load, with the load, right? So we'll try to make as less pulleys downwards. So that is what the normal, hints are there that how conveniently we can, put the system across, how to design a block and tackle system. Okay, so what we will do, the number of strands supporting the load will be 5. Let's see how we are, drawing the diagram. So here are 5 pulleys, 1, 2, 3, 4, 5. See, I have kept 2 in the lower one and 3 in the top one, not the other way around, right? And we started from here. Let me put a tackle if we have understood like 3 and 2, and then how to put a tackle. Let me use the red color. So we'll start from here because I want to pull downwards and I'll go block by block. So this I started from block, upper block, then lower block, then go to upper block again, come to lower block again, go again the another block and then come and tie it here. So can you see how many strings are there? So one is, let me see here. Let me zoom in if I can. Yeah. So, so here, how many strands are supporting the load? So this is the load downwards, right? This is the load downwards, and the number of strings are 5. So this is 1, this is 2, this is also supporting 3, this is also supporting 4, and this is also supporting 5. And for that, showing it clearly, we put small arrows also like 1, 2, 3, 4, and 5. So 5 strands are supporting the load. So the velocity ratio will be equal to number of strands, and those are 5. Let's get back. So efficiency, how we can calculate? We have calculated the velocity ratio, which is coming as 5 because 5 strands are supporting this load. And M may be calculated according to the data given of load and effort that came as 4.5. So for eta, we will divide MA divided by VR and we will get 9 by 10 or zero point 0.9. So our system is not ideal. It is not 100% efficient. It is not equal. It is 90% efficient. Okay, so there is some ground rules which we will discuss in the next question. Try to keep equal number of pulleys in movable and fixed block. If odd numbers are there, then keep the lower block with one less pulley. And I told you what is the logic behind that. We want to keep it as light as we can.